Hello, everybody. Let's see. Coming in on the end here. Uh, excuse me. Recording a lot of videos at once is hard on your voice. Good to know. Okay, so this is all about the two proportions. I'm going to try and knock out all this at once. Note, it's a lot like 1p, except you don't have to do as much. We don't have to solve for confidence. We don't have sample size considerations. It's just confidence intervals and hypothesis test, right? I want to mention, it will do the actual, like, changing the conclusions, rejecting H naught for you. You are better than this. You understand what it means when a p-value is less than 0.05. You don't need to type 0.05 in here and get it to tell you, yes, it is indeed less than 0.05. That said, you're welcome to. I think I'll do it on this example just to say that I've done it once. It's the exact same for this one. Little cutoff value for significance. It'll tell you whether or not it's literally telling you whether one number is smaller than another. So I think you guys are totally competent to do that. And that's why I haven't been using it so much on these tutorials. But it's here, same thing here with the 2 mu's, 2 p's, 1 p, it's there, same thing. So we'll use it this time and know that you can apply it to all of those other situations. Okay, these are all chapter 22 problems I'll be doing, so I know not everybody's there yet, and that's just fine. But you can come back to it when you need to. Okay. I've done a lot of video with chapter 1 example, or 21 examples. I might get into that a little bit on Friday. Anyway, I'm going to do problem 2 and problem 8. Okay, I thought this was a good one because it brings back our sampling distribution stuff. So let's see. We think that this campaign person has a problem with women voters. Campaign staff runs a poll to assess. They'll sample 350 men and 350 women, and they'll ask if they have a favorable impression. I wonder who this problem is talking about. Obviously, the staff can't know this, but suppose the candidate has a positive image with 61% of males, but only 55% of females. Complete parts A through E below. So, what kind of sampling is this staff planning to use? It is a stratified sample. We're randomly sampling from 2 different buckets. We're pulling random samples from 2 different buckets till we have equal numbers from each group, right? Yep, well done. Thank you, Pearson. What difference would you expect the poll to show? So, the proportion of people with a favorable impression of the candidate be some percent higher than women. So if we're taking this supposition to be true, there's a gap of 6% there. 6% higher among males. Yes, I know, Pearson. I just do so well. Of course, sampling error means the poll won't reflect the difference perfectly. What's the standard deviation for the difference in these proportions? Okay. I think it's time for the workbook. This is not the standard, or this is not an issue for this, right? This is wait a minute. 2 p's? I have 2 proportions. Okay. Okay. This is not the workbook to calculate a standard deviation from these 2 pieces of information. Instead, you've got to do, okay. let me just think about this. I think I will have to re-record this because it does give us the standard error. Okay, we're good to go. We're good to go. Let's do it. Let's do it. Let's do it. All right. I have to put a confidence in here so that it'll run the form. So I'll just put some confidence. So I'm going to take P1. So it's males minus females, right? So I'm going to take P1 to be the 0.61 there. P1 is the 0.55. N is 350. And N is 350. Okay. All right. So, standard deviation. And we'll have to be careful here. That's a 3-point enter to the nearest percent. That's a 4%. Yeah. There you go. Okay, sketch a sampling model for the size difference in proportions. Okay. So the trick here, right, is to focus in on the empirical rule, right? The mean will be 6%. Because we found it to be up here. Okay, there's only one of these that has a center of 6%, so we're done. Another thing to think about is that our standard deviation is about 4%, and 4% to either side, we see a 68% here. That is one standard deviation, the empirical rule for one standard deviation. So we have two reasons why we know that this is the only one that works. Or two reasons why that one's the one that works anyway. Okay, moving on. Okay. So, could the campaign be misled by the poll that there is really no gender gap? Choose the correct answer below. So, the idea is 0 in our confidence interval? That's one way to think about this question. 0 is 6 away from 6, right? So one standard deviation would be 4, two standard deviations would be 8, so it's a standard deviation and a half. Okay. So a poll result showing little difference would be 1 to 2 standard deviations below the expected outcome. Let's help our intuition a little bit here. What if I had a mean of 6? 0.6, that is. What if I had a, what if I had a 0.06 mean? If I had a 0.04 standard deviation? What's the chance that y is less than 0? Let's just ask. What's the chance that y is less than 0? 6% of the time. 6% of the time. So, the value 0 happens a little more than 5% of the time. So is it no, a poll result showing little difference is only 1 to 2 standard deviations below? Or is it yes, a poll result showing little difference is only 1 to 2 standard deviations below? It's the other one. That's how you know. 6 in 100 is not that unlikely. That's how I would know. There's a good chance they'll be misled. I mean, not a great chance, right? Most of the time they won't be misled by that, but a little bit of the time they will. Let's think about it in a slightly different way, like as a hypothesis test. less than, okay, we're testing for less than. Our null is that it is actually 0.06, right? Okay, successes, that's equals 350 times, so I'm doing NP, right, times 0.61 for our N1 is 350. Success is 2. That's another 350 multiplied by, in this case, 0.55. Okay, so there's our two proportions. And you'll note I forgot to put an equals in front of that. And there, now it's giving me a real number. Throw a 350 in here. Okay, that's all I have to fill out, I think. Oh yeah, not quite all, right? Because I have to less than successes p hat pooled. Okay. P hat from sample. From sample. That p-value is weird to me. Oh yeah. It calculates the difference right there. Or the standard deviation of the difference, that is. This is not very well suited to this problem, but let's look over here. This is another way to get at it. Let's make a 95% confidence interval. 0 is included in the interval, so it is likely to happen, likely-ish to happen. That's one way to put it, right? So they're making a standard deviations argument. Here's a confidence interval argument. 0 is included in the confidence interval, so it's likely. Probability get what you got or more in support. So this is only testing for a positive difference or more. We want to test kind of the opposite of that, right? And if we do that, if we take our complement of this number here, yeah, it is unlikely to observe this difference by chance. Yeah. Oh, geez. Let's take it one more step. What if I assumed and greater than like that? And these are my data. Ooh, the number's flipped, right? So now I'm saying, suppose it's 0. What's the chance I would have observed 0.6 by chance? And it's the same thing. Interesting. Okay. I'm going to leave it there. It's not it's 0's in the confidence interval, so observing no difference is pretty likely. Or you could say this p-value isn't less than 5, so it's pretty likely. Or you could say it's less than 2 standard deviations away, so it's pretty likely. 3 different ways to interpret that problem and get the same answer there. Okay, so let's do number 8. Yeah, let's see here. Examine parental influence on teenagers, a certain large region to smoke. From the regions who had never smoked were questions about their parents' attitudes for smoking. And they were questioned 2 years later to see if they were still smoking or if they had started smoking. Okay. So What kind of design is this? Um, so is it an experimental study? No, no, we're not controlling things really. Is it a retrospective observational study? Mm-mm. No, and the reason for that, the reason it's not a retrospective study is because we're not like prospective sounds like you're looking into the future, and I mean, yeah, you're kind of looking to the future, but really you're keeping track as it happens, right? You're not looking in the past, and that's why it's not a retrospective study. Okay. Um, we need to talk about these. Um, this is something we're going to talk about on Friday. Yeah. Anyway, so we want to rate an appropriate hypothesis. So the first thing we're going to say is that it's probably equal. They're probably actually equal, which means that the difference is actually zero, right? So P2 will be students who are lenient about smoking. That means, and we're expecting there to be more of them, right? So, okay, so the question is, do these data provide strong evidence that parents influences teenagers' decisions about smoking? So we don't actually know if they're influencing in a positive or negative way. We just know that there might be a difference. Okay. Um, are the assumptions and conditions necessary for inference satisfied? There are definitely more than 263 students with parents in the world, you know. Let's see, we have at least 16 that became smokers and 63 from the other group. So there's 10 and 10. Randomization. Well, let's see here. A randomly selected group. Excellent. All right, there we go. Okay, test the hypothesis and state the conclusion. So determine the test statistic. First step. Okay, let's run with it. Whoops, going the wrong way. Okay, so mhm, mhm. So okay, so our first thing, so P2 is P1, yeah, so P1 is disapproved of smoking. So that's that's the 63 of 263. 63 of 263. And the next one is going to be the 16 out of 45. Okay. We are assuming they're equal, and we're going to test to see if they're in fact not equal. Okay. Believe it or not, we're done already. Like we're done already. We're done already. There you go. P-value is almost 10%. Okay. Oh, we want to determine the test statistic. Ah, test statistic. That's a Command C for B. Command V over here, and 2 decimal places, so that'll round to 6.5. Yep, it's that simple. Once you have these yellow numbers figured out and you've got your hypothesis testing going in the right direction, it's just a copy paste from there. Find the p-value. I don't know, find it in the spreadsheet. Is that what they mean? Round to 3 decimal places. So that's going to be a 6. Except that's 4 decimal places. So what does this actually round to? The 6 rolls the 9 over, the 9 rolls the other 9 over, and that rolls it all the way to a 0.1. Jeez. And I actually want to look at that, I can't see the tolerance on that value. Oh well. State your conclusion. Use significance level alpha equals 0.01. Okay, so I said we'd do it right, so let's do it right. Cutoff value, 0.001. We failed to reject H naught. If this was 0.2, in other words, if our significance level was greater than our p-value, our alpha level, cutoff for significance equals alpha level. Your book uses the word alpha level. Yeah, so let's see that, right? If our significance was 11%, we would reject H naught. If it was 10%, we would still reject H naught. If it was 0.099999999, that rounded to 10. If it was 0.09, we would fail to reject. So the second we go below that p-value, right? The second our significance is less than our p-value, otherwise thought of as our p-value is greater than our significance, we fail to reject null. If our p-value, yes, back up here, we reject null, right? If p-value exceeds our significance, we fail to reject. All right. So at the 0.01 level, oh geez, I used 0.001. Well, 0.01. Have it. Still fail to reject. Reject. Do not reject the null. Okay. So they say do not reject, and there is not sufficient evidence. They say do not reject, there is sufficient evidence. There is not sufficient evidence. I know that because we were testing to see if these were actually the same thing. What's the likelihood that the difference we observed was due to chance? The likelihood is pretty high. So we do not reject the null, or we do not reject the null that there is in fact no difference between these two populations of teenagers. There we go. Okay. If the observed difference is the true difference, if there's no difference in the proportions, yeah. So you see the difference here. This is like saying in fact about stuff. This is saying there's a chance of seeing a difference due to sampling variation versus there's a chance that there's a difference, right? There's a chance that we observed a difference due to sampling variation versus there's a chance that there's a difference, period, right? Okay. So we were talking about error types on Friday, but a type 1 error is do not want to get this wrong. I just do not want to get this wrong. A type 1 error is when H naught is in fact true, but you rejected it. So we failed to reject null hypothesis, right? So we accepted the null. So if our conclusion was wrong, our conclusion was reject the null. If that was wrong, we would have rejected the null when it was in fact true. I'm sorry, we would have failed to reject the null when it was in fact false. So we rejected the null hypothesis. Or sorry, we failed to reject the null hypothesis. We accepted the null hypothesis when it was in fact false. That is simply defined as a type 2 error. There's two types. Because the null hypothesis is false, but it was not rejected. Okay. Create a 99% confidence interval. Why, don't mind if I do. Don't mind if I do. 99%. Boom. Oh, I gotta fill these in here. This is equals 63 out of 263. This is 263. This is equals 16 divided by 45. And this is 45. So the real neat thing about this, I think, is that we can compare two different sample sizes. Sorry, I'm waving my hands all over the place here. But yeah, these are two totally different sample sizes, and we can still make a reasonable comparison of the two. Okay, so create a 99% confidence interval. We need 2 decimal places in this number here. So that's how that one looks. Command C. 2 decimal places, so that would be an 8. All right, check answer. Thank you, Pearson. Yep. Yeah, so it's just a matter of filling out that form, right? Okay, so a researcher can be 99% confident that the proportion of teens whose parents disapprove of smoking who will eventually smoke differs from the proportion for teens whose parents were leaning about smoking by amount that is contained in the interval. What are the other options? Greater than, nope. Equal to, nope. Less than, nope. Contained in. Okay. Carefully explain what a 99% confidence interval means. Of all random samples of the population, 99% will produce intervals that contain the true proportion difference. Yep. Okay. All right. So I hope that will do for 2 P's. I will do one for 2 Mu's just as soon as I get that last one posted. And yeah, be well, guys.